The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. Alrighty, so today we're going to start chapter 9, which is about roots and radicals. And so let's get going. Okay, so this is section 9.1, part 1. We'll be spending 2 days on this. So I want to talk about the idea of roots. If I were to ask you, tell me about your roots. Am I asking you about your hair? No. What am I asking about? Your roots. What do I mean? Any ideas? No one wants to speak this morning.
Where you're from.
Where you're from, sure. So your roots are kind of where you're beginning, where you were from, where you were born, your heritage. All right. So kind of going back in time to where you started from. Okay. If we take, let's say, the number 3, and we square it, we get 9. So 9 is a square. It's a square of what? 3. So if we take the square, 9, and we say we want to go back to its roots, we say we want the square root of 9. So we're going back to the number that we squared to get 9 in the first place. So a square root is like undoing the square, going back to the original base. All right. So the square root of 9 is 3. Let me see if I can write that a little bit better. Okay. The square root of 9 is 3. There are some names that we need to become familiar with, vocabulary. This thing right there is called a radical. The quantity inside the radical is called the radicand. Okay. A radical is a grouping symbol. So it groups everything inside separate from everything outside. So let's say I have the square root of 7 plus 2. Well, you would start inside the grouping symbol, simplify that into the square root of 9, which then would become 3. Let's say I had 2 times the square root of 9. Well, that would be 2 times the square root of 9, which is 3, and then you'd get 6. So that radical is a grouping symbol. All right. Now, let's say that instead of taking a instead of taking a square root, we want to take the cube root of 8. So now we're looking for some number where that number times itself is 8, or that number cubed is 8. Well, the cube root of 8 is 2. But now we've introduced something that we didn't have back here. All right. This number is called the index. It tells you what root you are taking. So in this case, it's a 3. We want the third root, or the cube root. Back here, there is actually an implied index of a 2, meaning we want the second root, or the square root. But because the most common root taken in mathematics is the square root, and mathematicians are efficient, they use shortcut notation. So if there's no index written, it's an implied 2. All right. So the cube root of 8, this is the index, this is the radical, this is the radicand. Any vocabulary questions about those things at this point? All right. Now, 3 squared is 9, but -3, the quantity squared, is also 9. However, when we take the square root of 9, we only get the 3, which is called the principal square root. I can never remember whether it's AL or LE for principal. I think it's AL. Yes, it's AL. I was right. Okay. Now let's take a look at some examples. Let's say we have the square root of 100. So basically we're saying what positive number squared gives us 100? Well, that would be 10. So the square root of 100 is 10. On your calculator, your scientific calculator that you're supposed to have access to for this class, there should be a button that looks like this. It might be a regular key. It might be a second function key. You also might have a button that looks like that. Okay. This button is the square root button. This button we'll talk about a little bit later, but right now, this button. So if I want to find the square root of 100 on my calculator, I'm going to access that button. And if it's a second function button, then I need to push second and then that. Okay. On some calculators, when you do that, a left-hand parentheses comes up automatically. If that's the case, then you put in your 100, close it up with a right-hand parentheses, and push equals. All right. So if you have a calculator with you right now, try that. Make sure it's working. If it isn't, ask me about it. If you don't have a calculator ready, you're going to need access to one during this chapter quite a bit. So you should track that down. And if you have any questions about that, let me know. Okay. Now, let's say I want the square root of 75 plus 25. If I put that into the calculator, I am not going to get the correct answer. I need to quantify the radicand. So I need to, again, put parentheses around that entire radicand so it all gets sucked inside the radical. And again, this should give me an answer of 10. Okay. How about the square root of 49? Well, what times itself is 49? That would be 7. 7 times 7 is 49. How about negative the square root of 64? That negative sign is outside the radical. It's outside the grouping symbol. So starting inside the grouping symbol, the square root of 64 is 8. That comes outside, and then this negative sign hits it. So final answer, -8. Okay, now, let's say I've got the square root of -49. You can't take the square root of a negative number and get a real answer. So this is not real. In fact, you can't take an even root, whether it's the square root or the 4th root or the 6th root or the 8th root. You can't take an even root of a negative number and get a real number answer. Okay. That's one of 3 super important ideas in this chapter. So let me say it one more time. You can't take an even root of a negative number and get a real number answer. All right. Now, here, though, we weren't taking the square root of a negative number. We were taking the square root of a number, and then afterwards, the negative sign gets applied. Now, let's say we've got the square root of a fraction. Well, what's the square root of 4? 2. What's the square root of 25? 5. So the square root of 4 25ths would be 2/5, because 2/5 squared, which is 2/5 times 2/5 equals 4 25ths. All right. how about this? The square root of 0.25. Any ideas on that? What the square root of 0.25 would be? Nobody's volunteering this morning? Okay, well, let's see. 5 times 5 is 25. 0.05 times 0.05 would be 25, but then we'd have to come over. How about just plain old 0.5 times 0.5? Let's see, that's a 5 and a 2 over 2 places up, 0.5. Notice we're taking a square root of a number smaller than 1, and our answer is actually bigger than our original problem. Okay, well, let's look at this in terms of fractions. The square root of 1/4 is 1/2. Isn't 1/2 bigger than 1/4? So taking the square root of a number between 0 and 1, we get an answer that's larger than the original radicand. Okay. What about this? A negative outside the square root of -49. We can't say negative times negative is positive in this case, okay? The square root of -49 is not real, so even with a negative sign in front of it, it's still not real. So watch out for that. All right, now here is specifically a calculator problem. It says, find the square root of 12, give an answer to 4 decimal places. So on your calculator, the square root of 12, I'm getting 3.4641011615. But if I went it to 4 decimal places, that would be right there. The 5th decimal place, the 0 would round down. So my answer is going to be 3.4641. And let's do one more of those. The square root of 0.0063. Okay, the square root of 0.0063 is 0.07937253993. 4 decimal places would be right there. The 7 would round up. So I would get 0.0794. Any questions on that? Okay, moving on. This, let's see here, we have the square root of 4x squared. It says, simplify each expression, assume that all variables, in this case the x, are unrestricted, meaning x could be positive, x could be negative, x could be 0. So x could be any real number, okay? And use absolute value symbols when necessary. Okay, let me back up for a minute. And let's see here. Let's go back here. And I talked about that you can't take an even root of a negative number, okay? Which is why this is not real. Another rule, I said there were 3 big ones. The second one is when you take an even root, you can't get a negative answer, okay? And that actually goes back to this whole idea of the principal square root. So we've got, you can't take an even root of a negative number. And when you do take an even root of a positive number or 0, the answer can't be negative. So when you're dealing with even roots, if the index is a 2, 4, 6, 8, whatever, the radicand, the stuff inside, can't be negative, and the answer can't be negative. Okay? Now that's all with even roots. So We're told, back to this example, that x could be any real number. Well, the square root of 4 is 2, and the square root of x squared is x. However, we have a problem, okay? Since there's no index written, it's an implied 2. That means that this is an even root, and that means that the answer can't be negative. But we're told in the directions that x can be any real number. So if this x happens to be negative, 2 times that would be a negative answer. So what do we do to ensure that we have a non-negative answer? We put absolute value bars around the x. Now, since the absolute value of x can't be negative, 2 times that would have to be a non-negative number. How are we doing? Okay. Let's say I've got the square root of 64 t squared. And again, assume variables, no restrictions. T can be any real number. Use absolute value bars if necessary. So what's the square root of 64? That's 8. The square root of t squared is t, but just like the previous example, we would need absolute value bars to ensure that 8t is not a negative answer. Okay. Any questions there? All right, how about this? The square root of 36 y to the 4th power. Same instructions, assume there's no restrictions on the variable. So what would the square root of 36 be?
6.
Good. What would the square root of y to the 4th power be?
Would you get the square root of the 4, or how does that work?
No, we're taking the square root of y to the 4th. So what times itself would be y to the 4th?
Y to the second.
What?
Y to the second.
Yeah, I can barely hear you, but yes, y to the second. Now, back to you said, you take the square root of the exponent and it looks like that, but not exactly. All right, now my question here is, do I need absolute value bars around the y squared?
No,
No, we don't. Why not?
because there's a positive exponent, right? I don't know.
Well, it does have to do with the exponent. Okay, let's just say that y is negative. What's a negative times a negative? It's a positive. So since my exponent is a 2, y squared couldn't be negative. Therefore, 6y squared can't be negative. Therefore, I don't need absolute value bars. I know some of you are kind of going, what just happened? So this is 6y squared. Now, what about this? The square root of 9, y to the 6th power. What would that be? Or what's the square root of 9?
3.
Okay. What's the square root of y to the 6th power?
Would it be 3?
All right, good. Now, do I need absolute values bars around the y to the 3rd power?
No.
Yes, I do, because if y is negative, negative cubed would still be negative. And remember, we still got unrestricted. I know this is tricky. Do you see that though?
Oh, yeah.
One more example. I know. Time to break out the Tylenol. Okay. Square root of 4 n to the 8th power. All right. What's the square root of 4?
Two.
Good. What's the square root of n to the 8th power?
Four.
N to the 4th power. Do I need absolute value bars here?
No.
No, because n to the 4th power couldn't be negative. If n is a real number and it's negative, raised to the 4th power, it's positive. If it's positive, raised to the 4th power, it's still positive. And if it's 0, it's not going to be negative. So just be careful with these. Okay.
So
What's that?
Oh,
Question?
you can go ahead and go.
Okay. All righty. Let's see here.
So anytime it's it could be possibly a negative, you have to put the absolute value bars.
If you're taking an even root, okay. In fact, let's expand on that idea a little bit. So what if I'm taking the cube root of -8? Well, that's -2. Now I said you can't take an even root of a negative number. And if you take an even root, you can't get a negative answer. But with an odd root, anything goes. You can take an odd root of a negative number and you can get a negative answer because -2 times -2 times -2 is -8. Okay. So it has to do with even roots. You all right with that?
Yeah.
This is one of those things where you just got, it's like I'm going to dump all this information into your brains. And I know some of it's confusing. As you go through and do homework and get used to the idea, you'll get better at it. But at first it's kind of a shock, I know, especially this whole absolute value thing. All right, but those that have gone before you have survived. You will too. Take a look at this problem. F of x equals the square root of x. Okay. And we've got a table here that's got 0 and 1 and 4 and 9 and 16. Okay. Now, those x values aren't just random. Why do you think those specific x values were chosen for this problem? I didn't make them up. I got them out of the book. Why? What's special about them?
They're even and uneven. Or, I mean, even and odd, maybe.
Well, that's true. That's true. But I could have gone 1, 2, 3, 4, 5, 6, 7, 8 and still had even and odd. Well, let me ask you this. What's the square root of 0?
0.
What's the square root of 1?
1.
What's the square root of 4?
2.
What's the square root of 9?
3.
What's the square root of 16?
4.
All right, let's go back in here. Let's see. What's the square root of 2? Exactly. It's not so nice. These x values are all perfect squares, meaning when we unsquare them, we get nice whole numbers. Okay. So this makes it easy to graph, which is what we're going to do. Let's see here. I want to do that. Well, I'm just going to graph part of it. And let's see. So we've got, write this down. Hang on. So I've got 0, 0, 1, 1, 4, 2, and 9, 3. I don't want to go to all the trouble to switch screens. So I'm just going to go back here. And we've got 0, 0, 1, 1, 4, 2. And so this graph looks like that. Okay. And like I said, I could have switched screens, but I didn't want to bother with that for just one example right now. Okay, now let's go back here and then to that one. No, wait, I do want to go back there. Let's take a look at this picture again. Can you tell me what the domain of this function is? The x values that are included. Well, let me ask you this. What's the smallest x value there?
That would be 0.
0.
Does it include 0?
Yes, it should.
Okay. What's the largest x value there?
We can't
4?
quantify that because it goes infinitely.
Oh, no.
So infinity.
It goes up.
Okay,
Yeah.
like that. All right. What's the smallest y value?
That would also be 0.
And what's the largest y value?
Looks like it also goes infinitely.
Good, good job, Abel. There you go. So your domain and range of that particular function is from 0 to infinity, okay? Now, if you'll recall, this was f of x equals the square root of x. So the domain has to be 0 or larger. The range has to be 0 or larger. Well, we're taking an even root. You can't take an even root of a negative number. So x, the number inside, can't be negative. So it could be 0 or anything positive, 0 to infinity. When you take an even root of a number, the answer can't be negative. So the range, the output, has to be greater than or equal to 0. Do you see how this picture is fitting in with those whole restrictions? Okay. Let's say we've got this. F of x equals the square root of x plus 6. And I want to know what the domain is. So again, you can't take an even root of a negative number. So we're taking the second root. That means that the radicand, the stuff inside the radical, can't be negative. Well, if a number or a quantity can't be negative, then that quantity has to either be greater than or equal to 0. If it's greater than 0, it's positive. If it's equal to 0, it's 0. And if it's positive or 0, then it's not negative. And again, since we're taking an even root, the radicand cannot be negative. So I take the radicand, make it greater than or equal to 0, and solve this inequality. I subtract 6 from both sides, and I get that x has to be greater than or equal to -6. Writing that in interval notation, -6 to infinity would be the domain. Any questions on this example? All right, let's take a look at another example. G of x equals the square root of x plus 12. So how would you go about finding the domain?
Would it be x plus 12 is greater than or equal to 0?
Yes, indeed. Good job. Then what? What's your next step?
Subtract 12 from both sides.
Okay. And then,
And then is it -12 and infinity?
-12 to infinity. bracket around -12, parentheses around infinity. Good job, Carly. Okay. Let's take a look at another one. Are we good to go on? Are people getting this? Okay. H of x equals the square root of 35 minus 5x. So again, we're taking a square root. So what would we do now? How about just plain old ditto? The same thing we did in the last problem and the same thing we did in the one before that. Take the radicand, make it greater than or equal to 0. Okay. Solve the inequality. We'll subtract 35 from both sides. Oh, here we're going to divide by -5. What do you do when you divide both sides of an inequality by a negative number?
Switch the sign.
So we get x is less than or equal to 7. So the domain, we're going to go from -infinity up to and including 7. So for this problem, x can take on negative values, to which somebody says, well, I thought you said you couldn't take the square root of a negative number. We're not, because when x takes on a negative value, what's a negative times a negative? It's a positive, okay? So because of that, we're going to get negative values in our domain, okay? It's the whole radicand that can't be negative. That doesn't mean one little piece of it can't be necessarily. All right. How about, let's see here, t of a equals the square root of 3a plus 17. Okay. So again, we're taking an even root. So 3a plus 17 has to be greater than or equal to 0. Subtract 17. 3a greater than or equal to -17. Divide by 3. A greater than or equal to -17/3. So the domain, we're going to go, let's see, bracket -17/3, comma, infinity sign, parentheses. So everything greater than or equal to -17/3. Any questions on that one? Okay. Let's take a look.
Sorry.
No, go ahead. What?
So since it's still greater, the infinity sign is always going to be positive because it's going infinity towards the
Right,
other.
right, because it's greater than this, so it's going in that direction. Yeah.
Okay.
Good, good, good. Okay. Let's go back and let's look at f of x equals the square root of x. And we had 0, 0, 1, 1, 4, 2, 9, 3, 16, and 4. Okay. So we did that a little while ago and we graphed it. Okay. Now I want to consider g of x equals the square root of x plus 4. Now, I have a calculator. I could put in values of x and find the square root of 2 and 3 and 5 and all of that. But I want to do this problem without relying on the calculator to get approximations. I'm going to get nice whole numbers for my answer to graph it, okay? So consider this. Here, the radicand is x plus 4. So that means whatever number goes in for x, we're going to add 4 to that number, take the results, and find the square root of it. So now instead of me wanting X to be a perfect square like these, I want my X's to be 4 less than a perfect square, so that when I take that X value and I add 4 to it, I get a perfect square. Okay, so if we're going to add 4 here, my X values need to be what? 4 less than these. Let's see if you can follow what I'm getting at here. Okay, what's 0 minus 4?
0.
0 minus 4.
-4.
Good. What's 1 minus 4?
-3.
What's 4 minus 4?
0.
What's 9 minus 4?
5.
What's 16 minus 4?
12.
Great. Now, looking at those numbers, 0 is the only one there that's a perfect square, isn't it? But if we take those X values right here, we plug them in there, the first thing we do is add 4 to that original X. Okay, so what's -4 plus 4?
0.
What's the square root of 0?
0.
What's -3 plus 4?
1.
What's the square root of 1?
1.
What's 0 plus 4?
4.
What's the square root of 4?
2.
What's 5 plus 4?
9.
What's the square root of 9?
3.
What's 12 plus 4?
16.
What's the square root of 16?
4.
So to compensate for the plus 4 here, we took these values, subtracted 4 to get those numbers, and then we still got nice numbers. Now let's see what the graph of this thing looks like. Okay, so let me copy down some ordered pairs: -4, 0, -3, 1, 0, 2, 5, 3. Okay, and let's go back up here. We had -4, 0, -3, 1, 0, 2, and 5, 3. So there's our graph. But again, I got nice numbers. Do you see how we did that? Tell you what, let's do this a different way. Let's go back to here. G of x equals the square root of x plus 4. And let's just go ahead and pick, how about 0, 1, 2, 3, 4, 5. Let's just do that, okay? If x is 0, what's 0 plus 4?
4.
What's the square root of 4?
2.
If x is 1, what's 1 plus 4?
5.
What's the square root of 5? Well, let's see. What is the square root of 5? Okay. Square root of 5 is 2.236. Let's go with 2.24. So 2.24 approximately, okay? What's 3 plus 4? Oops, I wrote this in the wrong place. 2.24. Hang on. What's 2 plus 4?
6.
So this would be the square root of 6. And let's see, the square root of 6 is 2.45. So 2.45. What if x is 3? What's 3 plus 4?
7.
What's the square root of 7? Well, let's see, the square root of 7 is 2.65, approximately 2.65. What if x is 4? What's 4 plus 4?
8.
What's the square root of 8? Well, let's see. The square root of 8 is 2.283. And what's 5 plus 4?
9.
What's the square root of 9?
3.
Oh, finally, some nice numbers, right? Okay, well, my numbers here are awful. Let's see, 0, 2, 1, 2.24, 2, 2.45, 3, 2.65, 4, 2.83, and finally 5, 3. So I'm going to go back and I'm going to graph those points. Let's see. X is 1, Y is 2.24. Well, I guess that would be about 2.24. X is 2, Y is 2.45. It looks like my curve was a little bit too low there. And then 3 is 2.65. But could you imagine having to graph those without the line already there? Here, let's do this. Let's see. 0 is at 2, 1 is at 2.24, 2 is at 2.45. Not going to be as accurate as my other graph, is it? Okay. My point is, yes, it took a little extra work to produce. Let's see here. Where did we do that? These nice numbers. We had to subtract 4, but the result made it a lot easier to graph. Just something to think about as you're going through and graphing. Okay.
So if we have to do it like this, we just, instead of adding, we subtract.
What was the first thing you said?
For this one, so instead of adding, we will subtract.
Yeah, let's say you had h of x equals the square root of x minus 4. Then you'd add 4 to all of these to get perfect squares. In other words, you got to undo what's happening there. They took away 4, so we got to add 4 to the inputs. Here they added 4, so we have to subtract 4, just to make it easier to work with. Okay.
Yeah.
All right. Well, that's all I've got for you today. So let me stop the recording.